Alright, so part two, where you were talking about general relativity and how Einstein realized that mass warps space. And remember, he also came up with this all comes out of the same theory here, that energy is equal to mc squared, or that mass and energy are equivalent to each other. But remember, light is just energy. We realized that before, that energy is equal to h nu, and this is the frequency of the light, so, and this is just a constancy, whatever light you have is energy, then energy is equivalent to mass, so light actually has what we call a relativistic mass. If it has a relativistic mass, then it gets affected by the warping of space. Complicated way of saying that, if you have a large enough body, a body with enough mass, like our sun, then if you have a star back behind the sun, and you're over here looking at it, normally we couldn't see it because it's behind the sun. The starlight would run in the sun if it went in a straight line. But as the starlight goes close to the sun, it gets bent, and that star that was over here, we still see it even though it's behind the sun. To us it'll appear like that star's over here because we think, or we are assuming, that light goes in a straight line, but it's not. So anytime you have any kind of massive object, the light going by it will get bent by the mass of that object. Because the mass is warping the space, the light tries to take the most efficient path to our eye. Okay, when that occurs, that can be tested. So way back in the early 1900s, they said, hey, Einstein put out all this stuff. Let's go see if he's right. And so they went, and the only time you could see a star when there's a sun up is if you block the light from the sun. That only occurs during a total eclipse of the sun. During a total eclipse of the sun, the moon blocks out the light of the sun, and you can see stars right next to the sun. So what they did, astronomers early in the 1900s did, was they went and took pictures of stars during a total eclipse, during the daytime, right next to the sun, and they measured their position, and they figured out if their positions were in a different place than they were when they weren't close to the sun. And they found out they were off. They were off by exactly the amount predicted by Einstein. Einstein was right, that general relativity actually warps space. Nowadays we know it happens all the time. In fact, when you're using your GPS on your phone to do your location, the GPS satellites have to take into account the mass of the Earth and how it affects the timing of the satellites to make your position more accurate. If they didn't take into account the relativistic effects, it wouldn't be as accurate as the GPS position is. So relativity is even a part of everybody's life. It also occurs that when you're going close to the speed of light, remember time slows down. This is one other way that they proved that Einstein was correct, was they have accelerators now, the CERN accelerator over in Switzerland, where you can get particles up to about 99% of the speed of light. And then they round them into other particles. But these particles can be exotic particles that only last for like a billionth of a second, and then they fade away into other particles. But if you're going close to the speed of light, you can make that billionth of a second last to millionths of a second, or 1,000 times longer, because you're going so close to the speed of light, their time reference compared to ours is slowed down, and we actually see those particles exist for longer than they would in a normal environment. Only can happen is because Einstein is correct. There's another proof of Einstein too. If we go, this is the sun right here, and we have Mercury's orbit. This is highly exaggerated. But Mercury has an eccentric orbit, meaning it goes on an elliptical orbit. All the planets go on elliptical orbits. But under Newtonian mechanics, under Newtonian gravity, then it should just go on this elliptical orbit all the time. But under Einstein's theory of relativity, general relativity, which is another theory of gravity, says no, it will go on an elliptical orbit, but the elliptical orbit will rotate, so it's going to go around, and then it's going to go this way, and it's going to make more of a spirograph pattern as it goes around the sun. And so they went and measured the orbit of Mercury, and it exactly moves how Einstein predicted it. So we know Einstein is correct. All right, so now we get to black holes. So the idea is, since mass warps space or affects light, then you could have a, let me get another piece of paper here. You could have an object with more gravity. And if you had stronger gravity, then the light would get bent by more than it would on an object like the sun. The sun, our sun, barely bends light. It does bend it, but it's very small. So you'd have to have a more massive object in a smaller area. You got to concentrate the mass and make the gravity really strong. When you do that, then you get a stronger effect. And think of it like when you throw a baseball or something in the air. You throw a baseball up in the air, it falls back down again. If you throw it harder, it's going to go further and then fall back down again. But there's a point where if you throw it fast enough, it can escape the gravitational pull of the object. We call that the escape velocity. The escape velocity for the Earth is like 18,000 miles per hour. So to send anything to other planets, like to the moon or Mars or anything like that, we have to get that spaceship up to about 18,000 miles an hour. Otherwise it can't escape the gravitational pull of the Earth. Okay? All right, so that's what's called the escape velocity. That's how fast you have to go. Now the key to a black hole, and this is the definition of a black hole, is that the object has so much gravity, the density of it is so high, there's so much matter in here, that the light going out will fall back down onto the Earth. So that even if it's traveling at the speed of light, sorry, not to the Earth, to the black hole, it can't get away from the black hole. Or what we say is the escape velocity of a black hole is greater than the speed of light. That is the definition of a black hole. A point in space where the escape velocity is greater than the speed of light. Okay? Alright. How do you create a black hole? Well, there aren't many ways you can create a black hole. Right now, one of the only ways we can create a black hole is in a supernova type 2. Or what we call, we learned about these, the core collapse supernova. Now we talked about that in most supernovas, once it collapses, remember the core gets to iron and the iron collapses downward. It collapses into something only about 10 to 15 miles across. That's what we call a neutron star. But the problem with the neutron star is it's supported by the neutrons. Well, if you get enough neutrons together, even the neutrons can't support the gravitational field because the gravity gets too strong and the neutrons are destroyed. Okay? So, what we find is the mass of the remainder, or the remnant star, the mass, for a neutron star, it can't be, or the neutron star, mass of a neutron star, it must be less than 3 solar masses, or 3 times the mass of the sun, all combined into something that's about 9 kilometers across. All right, or 9 in radius, I should say. So this is a very small thing, about 10 miles across. If the supernova blows up, meaning it's a very high mass star, and that leftover core is greater than this, then when all the material collapses together, even the neutrons can't stop that collapse, and they all fall together and it creates a black hole. It's also when that black hole is created, in that final moments of creation of a black hole, that you can get a gamma ray burst. We talked about gamma ray bursters. And so it's as the collapse occurs and it goes past the neutron star stage into a black hole, you can send out a burst of energy, and that burst of energy is in gamma rays, and we call that a gamma ray burst. So, to create a black hole, they usually come from exploding type 2 stars, and they have to be very massive exploding stars. Okay? Alright, let's check my time here. Alright, so once you create the black hole, then does the black hole get bigger. Well, most of these start out at 3 solar masses. But every time more stuff falls onto the black hole, once it falls into the black hole gets more mass, and the black holes can grow. And you can get bigger and bigger and bigger black holes. And nowadays we see black holes that are what we call supermassive, on the order of millions of solar masses. Because over the 13 billion years of the universe, they've been just eating so many stars that they've become that big. Alright, let's talk about the effects around a black hole. Now, black hole, the truth is we don't really know what happens in here. This is a weakness in physics. Things all kind of fall apart once you get past that point. But there's a point inside, so we don't know what that's actually made of. We don't know if it's matter, if it's not matter. It could be just pure energy. Because remember, energy is equal to mc squared. So if you had enough energy in this tiny spot, it acts like it has mass, and it would just act like a black hole. So it could just be pure energy. We don't really know what's happening inside here. But there's a point around the outside where the escape velocity is exactly equal to the speed of light. Okay? That point has a special name. That's called the event horizon, or the Schwarzschild radius. That is the point of no return, where the escape velocity equals the speed of light. When you get inside here, the escape velocity is greater than the speed of light, and as you get outside, then it's less than the speed of light. But there's that point where you cross, and that's where the point where there's no return. Once you're past that point, you will never get back in. You can never get back at all. You're trapped forever. Okay? So, as you get closer to the black hole, your time slows down.